The objective of this exercise is to apply the transfer matrix method to a system which is dynamical system with mass m and a spring key. So the concept of transfer matrix has been intensively used in duct acoustics, for example, but here we will see that this is exactly the same for this problem. So for duct acoustics, for example, the dependence is a dependence in space, and in the present case we have a dependence in time. So let's have a few infos on the model. So we have a motion equation and mx dot dot plus kx equal to 0. My unknown is x. This is a function of t. And then we have two initial conditions. X in 0 is equal to x0, and x dot 0 equal to v0 is equal to v0. So these two numbers, x0 and v0, are known. And then when we apply the theory of ordinary differential equation, then we can find that this is a free vibration problem, no force here. And then the solution can be written as a linear combination of cosine omega 0t and sine omega 0t, where omega 0 is equal to the square root of k over m. So this is exactly what we have. So we see that everything is known in these two expressions because this x0 and v0 are given by the initial condition. Omega 0 is just given by the physical parameter k and m, and then we can know exactly what are x and v. We'll see now how to apply the theory of transfer matrix and exponential of matrix to this simple dynamical problem. So the first step consists in considering a state approach. So this means to replace this second order scalar differential equation by a first order vectorial with a vector s of t, which is a vector with two functions, and then to replace this equation by this differential system. So s of t, called the state vector, is in fact the juxtaposition of two functions, v of t and x of t, and then we have this system. So this has been done in another video, so I don't spend too much time on that. And then what we want to solve is this problem, s dot of t equal to this state transition matrix alpha, which is known, times s of t. And we have in parallel some initial condition that s in 0 is equal to v0 x0, and then this s of 0 is known because this is the initial condition. And we see that the initial condition that we have in the state vector are exactly the one that were given previously. So if we applied this, if we apply the concept of exponential of matrix, we know that s of t can be directly written as the exponential of t multiplied by alpha s of 0. Here we then have clearly the link between my initial condition s of 0 and the state of my system at time t. And this is given by a 2 by 2 matrix, which is this matrix exponential of t alpha. So this is a matrix exponential. The matrix exponential of a matrix which is my state vector, which is known by time t. Not that I just put t before alpha because it's more convenient to write that we have a number times the matrix than the matrix times the number. Even if it's the same, this is something that I used to do. And then this matrix t of t, which is in this case 2 by 2, is called the transfer matrix, and this is the objective of the exercise is to compute this transfer matrix and to compare with the solution of that we obtained previously by the theory of ordinary differential equations. The expression of the transfer matrix is given by the exponential of t times alpha, and the definition of the exponential of matrix is I2 plus t alpha. So this is the series expansion of my matrix when you see that I have some powers, successive powers of my matrix. So I just make a summary of what we have seen during the lecture. And one way to compute this expression is first to diagonalize the matrix alpha. So alpha equal to P lambda and P minus 1. If we look to this diagonalization, so this should be possible, and in fact most of the exercise will consist in finding P and lambda. If we just see to this expression of the diagonalization, we can see that, for example, alpha square is equal to P multiplied by lambda multiplied by P minus 1 multiplied by P multiplied by lambda multiplied by P minus 1. And then this P minus 1P is the identity, and then here we have matrix lambda square. And then we can generalize this expression to say that alpha at the power k is equal to P multiplied by lambda at the power k multiplied by P minus 1. So the expression of the transfer matrix is in fact P minus 1, so this is the identity, the first term here, plus T P lambda P minus 1 plus T square over 2 P lambda square P minus 1 plus so on. And this can be rewritten as P multiplied by the sum for k equals 0 until plus infinity of T at the power k multiplied by lambda at the power k over k factorial multiplied by P minus 1. So we can see here that this is the exponential of T lambda, because this is exactly the same formula where we have replaced alpha by lambda. And one main advantage when lambda is diagonal, so this has some values, lambda 1 and lambda 2, that we will compute later on, but then when we have a diagonal matrix, then the exponential of the diagonal matrix is the exponential of the diagonal term. So this is very easy to compute. And then the point is that when we have compute this diagonalization, we can obtain a very condensed form of the transfer matrix. So we then need to diagonalize the matrix alpha, and then for that we apply directly that alpha minus lambda times the identity is equal to minus lambda minus omega 0 square 1 minus lambda, and then the characteristic polynomial, which is the determinant of alpha minus lambda times the identity, is equal to lambda square minus plus omega 0 square. This, if we find to the root lambda, then we have that lambda is equal to plus or minus 1 I multiplied by omega 0, where I square is equal to minus 1. So this is the imaginary number. So we have the eigenvalues, and we can rewrite that lambda is equal to a number epsilon multiplied by I omega 0, where epsilon is equal to plus or minus 1. And then we will be able to compute both eigenvectors in just a single calculation. So if we compute this eigenvector, we can say that sigma, which is the eigenvector, is sigma 1 and sigma 2. We will find that alpha minus epsilon I omega 0 is equal to minus epsilon I omega 0 minus omega 0 square 1 and minus epsilon I omega 0 multiplied by sigma 1 sigma 2. We can find that these two equations are exactly the same. We just need to multiply by minus epsilon I omega 0 the second one, and we obtain the first one. And then we can find easily that sigma 1 is equal to epsilon I omega 0 sigma 2. In fact, this is also my lambda. And we can find that the eigenvectors are epsilon I omega 0 and 1 if we take the choice that sigma 2 is equal to 1. So in fact we have that lambda is equal to I omega 0 and minus I omega 0. So this is my diagonal matrix, and that sigma, which is our P, I call it P, is equal to I omega 0 1 and minus I omega 0 1. So now we have the diagonalization of the matrix alpha, because alpha, we know that this is P lambda P minus 1. But if we want to obtain the diagonalization and to compute the exponential of the matrix, then in fact we need to invert this P matrix. So this can be done very easily because this is a 2 by 2 matrix. So this is 1 over the determinant, so which is 1 over I omega 0 multiplied by 1 minus I omega 0 times 1, so this is 2 I omega 0. And then we have this 1 I omega 0, I omega 0, and minus 1. So you can see here that this coefficient goes here. So here we have the determinant. This coefficient goes here. This one goes here. And this keeps at the same place, but we change the sign. And this keeps the same place, and we change the sign. Now we have done the diagonalization of the alpha matrix, the state transition. We can just have a look to this sum, which appears in the previous slides. And this is the exponential of t multiplied by lambda. Okay, and then the exponential of t of lambda, we can take a real interest, which is that as lambda is diagonal, we can in fact rewrite the power of k just very simply because it remains diagonal, and we can put the sum entering into the matrix because we have convergence because of the factorial key, and this is in fact e to the I omega 0 t 0 0 e to the minus I omega 0 t. So in fact this sum can be written in a very condensed form where we see the exponential function appearing here. The difference between this and this is that in this sum, which is the sum here, this is the sum of scalar number. So the definition of the exponential function for scalars. And then this part can be written in a very condensed form where we have dependence on time in e to the I omega 0 t and e to the minus I omega 0 t, which is something which sounds familiar for every acousticians. So now we are very close to the expression of the transfer matrix, because we have the product, the following product to compute. And then here we can first rewrite that this is this constant here that I can put in factor of everything. So the product of the first two matrices, we see that we multiply by a diagonal matrix on the right, which means that in fact we can multiply the column. So here you see that I multiply the second column by e to the minus I omega 0 t. So this is the product of the first two matrices. Then I have to, then this is just the remaining part of p minus 1. So this is 1 over 2 I omega 0 multiply by, so here I omega 0 multiplied by e to the I omega 0 t plus e to the minus I omega 0 t. So we have this minus and this one. And then here we find a formula which is very close. So for the the coefficient at the second line and first column, this is e to the I omega 0 t minus e to the minus I omega 0 t. For the 1, 2 coefficient, this is minus 0 square e I omega 0 t e minus I omega 0 t. And here we have I omega 0 e I omega 0 t plus e minus I omega 0 t. This matrix can be simplified because we can see here that, of course, I omega 0, which is here, can be simplified, for example, with this one, and we have e I something plus e minus I something divided by 2. Then this is a cosine, and we can rewrite after calculation that this is, so here we have a cosine of omega 0 t. For the second term, we have minus omega 0 sine of omega 0 t. For the 2, 1 coefficient, then this is sine of omega 0 t divided by the omega 0, and here we have cosine of omega 0 t. So here we have the expression of t, which is the transfer matrix. So the final step is just that we have the expression of the state vector at time t, s of t, which is the product of the transfer matrix, which depends on t times the vector of initial condition. So this is v0 and x0. And then this s of t is equal to v of t and x of t. And then when we just make the product of this matrix by the vector of initial condition, we find that v of t is equal to cosine of omega 0 t multiplied by v0 minus omega 0 x0 multiplied by sine of omega 0 t, and x of t, which is equal to v0 over omega 0 sine of omega 0 t plus x0 cosine of omega 0 t. And these two expressions here are exactly the one that we obtained by the other method. So we have seen in this exercise that with transfer matrix we can compute exactly the solution of the problem with a method which is a bit different.